In this section, we're going to talk about the derivatives for exponential and logarithmic functions. And I apologize, I had an error on the heading for these notes. I forgot to change it when I copied over from the last section. So this is section 3.9, and we'll be doing derivatives for exponential and logarithmic functions. So let's start with the derivative for exponential functions. First, we're just going to look at base e. So the derivative for e to the x happens to just be e to the x. And if you want to see a nice detailed explanation for this, take a look at the book. It goes through an explanation that should help you believe that this is true. But the derivative for the function e to the x is just that function itself. And if we have e to something else, like say e to the x squared or e to the cosine of x, the derivative for that combination where we have e to a function, we start the same way. We would do e to that function, but then because this is a composition, we need to multiply by the derivative of the inside, which would be technically the derivative of the exponent. So this is just the chain rule when the exponent is not just x. So when the exponent is just x, the derivative of e to the x is e to the x. When we have e to a function of x, then we would have the derivative as e to that function times the derivative of that function. So let's use that in example 1. So find the derivative of f of x equals 3x squared plus e to the sine of 3x. So now we want the derivative, so we'll write f prime of x equals, and the first term is just a polynomial, so we'll do 3 times 2x, so that's going to be 6x, and then we'll add the derivative of e to the sine of 3x. So we notice that fits this structure where we have e to a function, and the theorem says the derivative is e to that function times the derivative of that function. And notice that function, sine of 3x, is another composition. So when I do its derivative, I also need the chain rule. So I'll have the derivative of sine is cosine. I'll leave the input the same, and then multiply by the derivative of the input, which would be 3. So what we find here is that the derivative, f prime of x, is 6x plus, I'm going to reorder this, 3 cosine of 3x times e to the sine of 3x. And it was fine in the order it was written before. It's just conventional to put the coefficient in front, and then anything that's a factor that's not with the exponential piece would also go in front, just to make it clear that that cosine of 3x is not up in the exponent. So there we go. Next one, find the derivative of f of x equals x cubed times e to the 5x plus 1. So here I can see I'm going to need the product rule, because when I read that, I had a times in the mix there, right? We've got a product, so product rule, and then we'll also have a chain rule just when we differentiate the e to the 5x plus 1. So this time, f prime of x, I want the first times the derivative of the second, and again I'm just going to sketch this out, plus the second times the derivative of the first factor. So this is going to look like x cubed times, and then for the derivative of e to the 5x plus 1, I say, okay, I'm going to do e to the 5x plus 1 times the derivative of the exponent, so times 5. And then on this second term here, we have plus e to the 5x plus 1 times the derivative of x cubed, which would be 3x squared. And again, we could just rewrite this to make it look a little nicer. So I could say this is going to be 5x cubed times e to the 5x plus 1 plus 3x squared times e to the 5x plus 1. And you can see we could factor out an e to the 5x plus 1 if we wanted to, but this is just fine. All right, then example 3 gives us a function that's modeling a mosquito population after t days, and we're asked what is the rate of change of a of t after 4 days. As soon as we see rate of change of something, that means we want the derivative of that thing. So rate of change of a of t would be a prime of t, and we want to know specifically what's the rate of change when t is 4. So first we'll find the function that gives us the rate of change after t days, and then we'll plug in t equals 4. And we can see this function is just a multiple, a constant multiple of an exponential function. So this time we don't need a product rule. We'll just use the scalar multiple, or the constant multiple 100, times the derivative of e to the 0.3 times t. And the derivative for that will be e to the 0.3 times t times the derivative of the exponent, which is 0.3. So if I multiply the 0.3 and the 100 together, that'll give me, what, 30 e to the 0.3 t. And let's think about the label on that. This would be in mosquitoes per day. So 3 times e to the 0.3 t mosquitoes per day. And when t equals 4, we'll have 100 e to the 0.3 times 4 times 0.3. I could have used my simplified form, so 30 e to the, let's see, that's 1.2. Let's get an estimate of that value here. Let's see. Grab my calculator. So we wanted 30 times e to the 1.2. So about 99, roughly, mosquitoes per day. Would be the rate of change after 4 days. All right, then moving on to the derivative for the natural log function. Here we say if x is greater than 0, because that's the domain for the natural log function. So for values of x that are in the domain, then the derivative of that function is 1 over x. And if instead of just natural log of x, I have the derivative of natural log of a function of x, I'll do 1 over that function times the derivative of that function. And again, this is just the chain rule for input f of x, not just x itself. And we can prove this using implicit differentiation applied to the relationship x equals e to the y. Because remember, if y equals natural log of x, that's the same thing as e to the y equals x. So if I differentiate both sides, I'll have e to the y times dy dx on the left side, and I'll have just 1 on the right side. So this is differentiate both sides with respect to x. So doing the implicit differentiation that we talked about in the last section. And now I want to solve for dy dx. So I'll have dy dx equals 1 over e to the y. But then remember that e to the y is the same as x. So I can replace this e to the y with x. All right, so we can see the derivative for natural log of x is just 1 over x. So in example 4, I want to find the derivative of natural log of a function. And so we say, okay, we need the chain rule, which would tell us the derivative is 1 over whatever's inside, whatever this input is, so x to the fourth plus 2x squared plus 3 times the derivative of the input to the natural log, so times 4x cubed plus 4x plus 0. And if you want to, you can write that as a single fraction, 4x cubed plus 4x in the numerator, and then x to the fourth plus 2x squared plus 3 in the denominator. Right? So anytime you have the natural log of a function like this, when you simplify your derivative, you should have the derivative of the input as the numerator and the input itself as the denominator. In example 5, we want the derivative of this function that's a natural log with a more complicated input. And they're giving us the suggestion, first use the properties of logarithms to just simplify before we do the derivative. So if you think about the input here, the input is a quotient that also involves a product. So if we were going to multiply by the derivative of the input, it would get pretty complicated. So rather than straight away saying, let's just do the derivative for this natural log and then the chain rule time multiplying by the derivative of the input, we'll simplify the natural log first. And what you want to remember is the natural log of a quotient is the difference of the natural logs of the numerator and the denominator. So we can split this first into this difference of natural logs. And then we could say, let's see, the second term here has a product as the input for a natural log. So we could rewrite that a little bit. And we could rewrite that as the natural log of x cubed plus the natural log of cosine of 3x. You want to be very careful and realize that the cosine of 3x is a group altogether. It's not two separate factors, right? It's not cosine times 3x. So we can't break that apart, but we can at least split up these two factors of x cubed and cosine of 3x and then have two separate logarithms added together. Right? And we're supposed to subtract both of those factors or both of those terms since they were both originally factors on the input and the denominator. So if we simplify a little bit further here, we would actually have natural log of x cubed subtracted and natural log of cosine of 3x subtracted. And then we could say, well, remember there's another rule that says instead of natural log of x cubed, I could write this as 3 times the natural log of x. So we could take that step. And then if we really want to go even further, we could notice that the first group here, this is just x factored out times x plus 3. So we could rewrite that group as the natural log of x plus the natural log of x plus 3. And then we could observe that we have a natural log of x minus 3 natural log of x. So we could call that negative 2 times the natural log of x. And then I think we've done all the simplifying we can before we take the derivative. So again, this is still just the function itself. And rewriting the function using logarithmic properties as much as we can. So now that we've got this form, the derivative won't be so bad. We'll say the derivative is going to be, the negative 2 on this first term is just a scalar, so negative 2 times the derivative of natural log of x, which is 1 over x, plus the derivative for natural log of x plus 3, so we would do 1 over x plus 3 times the derivative of x plus 3, which is just 1, minus the derivative for natural log of cosine of 3x, which will be 1 over cosine of 3x times the derivative of cosine of 3x, which is the derivative for cosine first, so negative sine, leave the input alone, and then multiply by the derivative of the input. And then just cleaning this up a bit, we'll have the derivative is negative 2 over x plus 1 over x plus 3. Let's see, we have a subtraction and also a negative factor on sine. So let's say plus 3 sine of 3x over cosine of 3x. So we could call that tangent of 3x if we wanted to, but I'll just leave it like this. And then on the next page, we have derivatives for bases other than e. So log base 5, for example, or 5 to the x. So far we've only looked at e to the x and then the natural log, which is a log base e. So here, if we have a base that's positive and we never have a base equal to 1, but so for bases that are positive and not equal to 1, and if g is a differentiable function, we say the derivative for the log base b of x is 1 over x like it would be for the natural log function, but then with an extra factor in the denominator of natural log of b. And then if I have the derivative of the log base b of a function of x, I start the same way as I would with natural log. I do 1 over the function, and I also have times the derivative of the function, but again, in the denominator I have that extra factor of natural log of b. And then if I have an exponential function with a base that's not just e, so base b, I say its derivative is b to the x, but then I multiply by an extra factor of natural log of b. And similarly, if I have the derivative for b to a function of x, the derivative is going to be b to the function of x times the derivative of the exponent, and I have a typo here. I need my extra factor of natural log of b. So be sure to add that in your notes. Okay, so now if I want the derivative of this function, h of x equals 5 to the x plus 3 over 4 to the x minus x squared, I'm going to use the quotient rule because I have a quotient here, and I'll have h prime of x equals, and I want to use low d high minus high d low over low squared. So low here is 4 to the x minus x squared. D high, the derivative of the numerator, will be the derivative of 5 to the x. So 5 to the x, just like I would start with e to the x, times the natural log of the base, so times natural log of 5, plus the derivative of 3, which is 0. And then I want minus high d low, and d low would be the derivative of 4 to the x, which would be 4 to the x, times the natural log of the base, which is natural log of 4, minus the derivative of 2 or x squared, which would be 2x. And I want to make sure that I put that in parentheses so that I get the numerator multiplied with the entire derivative of the denominator. So that should be the numerator of my derivative, and then in the denominator I just want the denominator squared. So the original denominator not differentiated, just as it was with the square. And we don't need to clean that up. We'll just leave it just like that. So we needed a quotient rule, and then we needed the derivative for an exponential function that had a base other than e. Example 7 asks us to find the slope of the tangent line to the graph. And remember, the slope of the tangent line to the graph, that's just the derivative. So we want the derivative dy dx evaluated at x equals 9. So first we'll find the derivative at any value of x, and then we'll plug in x equals 9. So let's say dy dx would be, if this were natural log, I would do 1 over 2x plus 7, 1 over the input, times the derivative of the input. And because this was a base that wasn't just e, we'll have an extra factor in the denominator of natural log of 5. So let's clean this up a bit. We'll have dy dx is 2 over, and I'm going to put the natural log of 5 in front, times 2x plus 7. So when x equals 9, we could write this as f prime at 9 would be 2 over natural log of 5 times, let's see, 18 plus 7, so 18 plus 7 is 25. So the slope of the tangent line would be that value. If we wanted the equation of the tangent line, remember we do y equals the derivative at 9 times x minus 9 plus the function value at 9. So we'd have y equals this slope times x minus 9 plus log base 5 of 25. And that would just be 2, right? Because 2 is the exponent you put on 5 to get 25. So we could clean that up as y equals 2 over natural log of 5 times 25 times x minus 9 plus 2. All right. Then the last thing we need to talk about in this section is how to deal with the derivative of a function when both the base and the exponent are variable. So far we have rules for if the base is variable, like x cubed or x to the 5th, and if the exponent is variable, say like e to the x or 5 to the x, but we don't yet know how to deal with something like this, x to the x, where both the base and the exponent are variable. So x to the x would be a simple case. Example 9, we're going to look at x plus 2 to the sine of x, right? So anytime I have a variable showing up in the base and in the exponent, we need to use this technique, right? And this is called logarithmic differentiation. And so the steps are outlined here. We're going to take the natural log of both sides, and that's going to give us the natural log of y equals the natural log of some function. And we'll use properties of logarithms to expand the natural log of h of x as much as possible. We'll differentiate both sides, and then we'll have, on the left, you'll see we'll always have 1 over y times dy dx, and then we're going to solve for dy dx. So let's keep that list handy, and let's take a look at finding the derivative of y equals x to the x. So anytime we have this situation where we have a variable base, variable exponent, step 1 is take the natural log of both sides. So we're going to say the natural log of y is the natural log of x to the x. And this side we will be able to rewrite using the logarithm property that says I can move that exponent out from the natural log input and make it a coefficient. So now I'll have x times natural log of x instead of natural log of x to the x, right? And this is good because now I have something I can differentiate. I know how to differentiate x, I know how to differentiate natural log of x, and I know how to differentiate a product. So I just need to be careful to remember product rule. And on this side, I need the chain rule, because I don't just have natural log of x, I have natural log of a function of x. So I need to do 1 over the input times the derivative of the input. So there's the derivative of the left side, and that's going to be the case every single time. The derivative for natural log of y will be 1 over y times dy dx. And the right side, we're going to, like we said, use the product rule. So I'll have the first times the derivative of the second, which would be 1 over x, plus the second times the derivative of the first, which is just 1. And then I want to solve for dy dx, which is going to mean multiply by y on both sides. So I have x over x, which reduces to 1, plus natural log of x times y. So if we clean that up, now we're going to have 1 plus natural log of x times y, but I don't want to leave the y here. I always want to go back to y as a function of x. So that would be x to the x. So we landed at the derivative of y with respect to x is 1 plus natural log of x times x to the x. And these steps will be the same every time we have this kind of problem. So take the natural log of both sides, simplify the logarithm on the right side, differentiate both sides, being careful with implicit differentiation on the left side, and then multiply both sides by y. So let's look at one more. Find the derivative of y equals x plus 2 to the sine of x. So again, we notice variable base, variable exponent. So right away, we're just going to take the natural log of both sides. And on the right side, I'm going to move the exponent down. So I'm not taking a derivative here, I'm just doing a property of logarithms. And on the left side, I haven't done anything. I just have natural log of y, just still rewriting. And now I differentiate both sides. On the left, I have 1 over y times the derivative of the inside, which would be dy dx. And on the right side, I need the product rule again. So first times the derivative of the second, and natural log of something, I do 1 over that input times the derivative of the input. And then we want plus the second times the derivative of the first. The derivative for sine of x is cosine of x. So we're done differentiating, and now we multiply both sides by y to solve for dy dx. So I'll have dy dx equals, let's see, sine x over x plus 2 plus cosine of x times natural log of x plus 2. I'm not sure why I changed the order there, but I did, times y. And then we can replace y with x plus 2 to the sine x. So I'll have dy dx equals this stuff times x plus 2 to the sine of x. You always want to get back to x's when you can. And anytime you start with this form, variable base and variable exponent, you'll be able to get your derivative just in terms of x. All right, then the next one, we have again a situation that doesn't necessarily require logarithmic differentiation. We don't have a variable base and a variable exponent, but it can be a much simpler derivative if we use logarithmic differentiation. So when you have a fraction like this and you can see you've got products involved in either the numerator or the denominator and radicals, oftentimes if you take a minute to just take the natural log of both sides and rewrite before you differentiate, it will make your derivative much easier. So as a first step, we'll take the natural log of both sides. So I'll have natural log of y on the left side, and on the right side I'll have natural log of x cubed times x squared plus 3x minus 1 over the fifth root of x squared plus 2. All right. And so on the left side, we're just going to leave that alone for now, but on the right side, we're going to do a little bit of rewriting. And we can say, well, I've got a quotient, so I'm going to say I've got the natural log of the numerator minus the natural log of the denominator. And then in the first term here, I also have a product, so I'm going to break that up. And if I have the natural log of a product, I can make that the sum of the natural logs of the inputs, over the two factors. And then I'm going to remember that a fifth root is the same as an exponent of 1/5. And the reason I want to be thinking about that is that I know I have another logarithmic property that says I can move those exponents down. So now I've got, let's see, the first one, I'll move the 3. So I'll have 3 times the natural log of x plus the natural log of x squared plus 3x minus 1. And on the last term here, I'll move the 1/5, natural log of x squared plus 2. All right, and now I don't have any multiplication or division or radicals inside the logarithms. I have sums and differences, but there's nothing I can do to rewrite those. So now I'm at a point where I can differentiate both sides. So now I'll have 1 over y times dy dx from the chain rule on the left side. And then 3 times the derivative of natural log of x. So 3 times 1 over x. I'm just going to right away write that as 3 over x plus 1 over the input times the derivative of the input. So I'm going to put that just right away in the numerator. That would be 2x plus 3 minus 1/5 times 1 over the input on this last one, x squared plus 2, times the derivative of the input, 2x. And then the last thing is we want to solve for dy dx. So we'll have dy dx equals, and this is going to all stay the same, so 3 over x plus 2x plus 3 over x squared plus 3x minus 1 minus 2x over 5 times x squared plus 2 all times y, and I'm going to go ahead and right away rewrite y as x cubed times x squared plus 3x minus 1 over the fifth root of x squared plus 2. So there we have the derivative using logarithmic differentiation. So again, we didn't need logarithmic differentiation in this problem, but it definitely made the derivative a little bit cleaner. In examples 8 and 9 on the previous page, we didn't have a way through those without logarithmic differentiation. So sometimes it's required, and then sometimes it's just helpful, as in example 10 here. All right, then example 11 says the number of cases of influenza in New York City from the beginning of 1960 to the beginning of 1964 is modeled by this function. It looks like I have an extra inequality symbol there, where n of t is measured in thousands and t is measured in years, and t equals 0 corresponds to the beginning of 1960. The first part just asks us to evaluate n of 0 and n of 4 and then describe what those values tell us about the disease in New York City. So n of 0 and n of 4. We're going to need a calculator, so grab your calculator. And we have then 5.3 times e to the 0.09 times t squared, so times 0 squared for the first one, minus 0.87 times 0. So that's just going to give us an exponent of 0, which means e to the 0, that's just 1, so we get 5.3. We could have done that without a calculator. I wasn't thinking. And n of 4, we'll have 5.3 times e to the 0.09 times 4 squared, so times 16, minus 0.87 times 4. So we get 0.689. So if you think about these values, these would be, it said n of t is measured in thousands. So this tells us when t equals 0, so at the beginning of 1960, about 5.3 thousand people had influenza. So we'll say 5,300 cases of influenza. And let's see, in 1964, at the beginning of 1964, there were 0.689 thousand, so that would just be 689 cases of influenza. So the function values just tell us the number of people, they don't tell us the rate of change. But what we can see is that definitely the number of cases decreased between 1960 and 1964. So we would probably expect that the derivatives, at least the derivative at 0, should be negative. Maybe the derivative at 4 is also, we don't know where it's headed from there, but we can see that there was a drop between t equals 0 and t equals 4. So we would guess that at least somewhere in between there was clearly a decrease. Maybe it wasn't decreasing right away. That's what we'll kind of find out here when we look at n prime of 0 and n prime of 4. So let's first find n prime of t, and that's an exponential function with a variable exponent that's not just t, it's a function of t. So we'll have 5.3, that constant multiple, and then e to this function just as it is, times the derivative of the exponent. And the derivative of the exponent would be 2 times 0.09, so that's what, 0.18 t minus the derivative of 0.87 t, which would be 0.87. So that's the derivative at any value of t. So n prime at 0 will be 5.3 times e to the 0, which we already saw from the first part, times 0.18 times 0 minus 0.87. So times 0 minus 0.87. All right, so that's going to be what? Negative 0.87 times 5.3 times e to the 0, so times 1. So we can see this will be a negative value. And n prime of 4 is going to be 5.3 times e to the 0.09 times 16 minus 0.87 times 4 times 0.18 times 4 minus 0.87. So let's see what we get for those values. So we've got negative 0.87 times 5.3, so negative 4.611. For the first one, and then 5.3 times e to the 0.09 times 16 minus 0.87 times 4 times 0.18 times 4 minus 0.87. So we get negative 0.103 roughly. Right? So what we can see here is that the number of cases, I'm going to interpret down here, in 1960, the number of cases of influenza was decreasing at a rate of this many thousand per year. So let's say 4,611 cases per year, if we switch that number to thousands. And then in 1964, the number of cases was still decreasing, but by a much smaller amount. So then in 1964, the number of cases of influenza was decreasing at a rate of let's see, 103 cases per year. All right, so again, focusing on the difference between the labels for the original function and the derivative, and then being able to interpret what those numbers are telling us. So hopefully this section is helping you understand how to do the derivative for an exponential function and a logarithmic function. And that should be it for our new function types for differentiating.